what is this function looks like? Here's a interesting answer. So if m equals to 1, it is a multiplication of power law functions. And if m equals to 2, the major G function has this form, and here is a Gauss hypergeometric function here, which is expressed in this way. So you can see it. Yes, you can see it. If m is getting larger, the form seems like it's getting more and more complicated, but actually it's not. So for n greater than 2, n is an integer number, and the major G function has this form where the parameters are defined like this. So that's what is major G function looks like. So it's a kind of combinations of power law functions. Then here we defined the multi-ek integral of generalized fractional order operator, and then the major G function. Here is a relationship of the major G function with the multi-ek integral operator here. Why we use major G function as a here is because almost every special function could be expressed by the special cases of Fox H function or the major G function. So the generalized integral of this generalized function is a kind of meaningful conclusion here. And the equation 11 shows this relationship. As I said before, all the above parameters, equation, and variables should be well defined, or else there will be problems, there will be troubles, especially in the time domain and the integral domain, something like this. There will be a lot of troubles if we don't well define these parameters. So here is a generalized fractional order integral here. You remember in classical fractional order calculus, the fractional order derivative and then a fractional order integral is an identity transfer. So in the generalized fractional order case, what is the inverse transform of this generalized integral operator? Here is the answer. So you can see here, the GZ here is a generalized multi-ek integral of function fz, which is shown here. And then the original function fz, here z equals to x with power 1 over beta. So fz is equal to this equation, which is shown here. That is 2c. There is still a kind of inverse transform of generalized multi-ek integral. So maybe we can define this kind of operator here be the generalized multi-ek derivative. Maybe it's only a kind of good try. It's still not the conclusion. So for the multi-ek generalized operator, there are seven properties. The first one is here. That is to say a power law function multiplies fx, then applied multi-ek operator here. This equation holds well. So you can see that the power law function is sorry, it should be uppercase. It should be like this. I use the underscore here. So the other property is about the initial values. In in fractional order calculus, especially in the fractional order equations, if the initial values are not defined well, we cannot get the unique solution of the equation. So in generalized fractional order calculus, there is one kind of formulation of the initial values, which is shown in equation 14. Here, Cg, this constant is really important in GFC. Here, the integral of this part with G's order derivative, the value at 0 at the origin equals to this one, which is related to the integer order derivative. Property 3 is defined like this. This property is really interesting. That is to say, you see, we define an operator like this form, and then equation 15 holds. That is to say, the inverse of this operator applied to this equation equals to this one. It is very interesting conclusion because associated with this property, we can get a lot of interesting results, like the how to solve.
Come back.
Yep.
X is a vector in equation 14.
Yep.
X is a vector, and what about the upper J?
G's order derivative, integer order derivative.
Not derivative.
No.
Derivative, not derivative.
Derivative?
Derivative.
Derivative.
Yes. Integer order derivative.
Integer.
Yeah.
You know, fx is a function. It's not a vector valued function.
Yeah, I know your problem. Actually, there's an interesting thing here. That is to say, you say, here is a G's order derivative, right? Here is another G's order derivative. And Cg here is a constant. F0 is still a constant. That is to say, the whole part in this bracket should be another constant. So
I mean that J means the differential order, right?
yes,
Differential order.
yeah,
And x is a vector, right?
yes,
Fx is a vector value function, right?
yes,
How to define?
yes. It's true. It's always a kind of mapping. So it's always a linear mapping here. So from real domain to real domain. Yeah.
But you have a x, you have a 0. You are saying x equal to, I mean, you first find derivative, then x equals to 0. Then you shouldn't do like that. I mean, just put a
Yeah.
bar there and say x equals
Okay,
to
okay. I'm doing it now.
After differentiation, set the x equal to 0 is no problem.
No, I mean his expression.
Yeah. Okay.
Yes,
Okay.
yes.
I'll polish it. Okay.
Looks like, I don't know what's this.
Looks like weird, right? Okay. I'll polish it.
Oh, you know somebody else have used this kind of expression.
Yes. Okay. So the false okay. Here is a false property. Is a kind of commutative law of the generalized fractional order ek integral. Here, you remember there is a semi-property of the fractional order operators in the classical cases. Here, in the generalized multi-ek definition, we still have this kind of forms, which is shown in 16. You see here, I, tau k, sigma k is on the left side, and then it is transferred to the right side. And the multiplication of these two prime operators are equivalent. The fifth one is a semi-group property as a multi-ek integral. The form is